Good morning, everyone. Welcome to the 2021 Houston Tech Rodeo Aerospace Space Track. And our fourth presentation today is with Dr. Harold Sonny White. And we will be listening to Dr. White talk about achieving interstellar travel. Sonny, excuse me. Thank you for participating today, and I'll let you go ahead.
Okay, copy all. Sounds like you're enjoying that fine Houston weather, the pollen in the rain, right? So, hey, thank you, Paul. Appreciate the introduction. Let me share my screen here. Thanks everybody for joining today. It's great to get a chance to talk to folks about bold space exploration. Let me share my screen there. Okay, hope everybody can see that. So I'll be talking to you guys today about Limitless Space Institute and specifically the very audacious goal of trying to achieve interstellar travel. It's a pretty big objective. But first, let me tell you a little bit about Limitless Space Institute. Limitless Space Institute is a 501c3 nonprofit here in Houston. Founded a couple years ago by Dr. Cam Gafarian and Brian Kelly. And so I joined them as the Director of Advanced Research and Development after 20 years at NASA, kind of working in advanced power propulsion. And so Limitless Space Institute, our mission is to inspire and educate the next generation to travel beyond our solar system and to support the research and development of enabling technologies. Our pinnacle objective, our North Star, if you will, is to try and work towards enabling interstellar travel by the turn of the century. And that is by no means an easy feat. It's unbelievably difficult. You know, when we think about space exploration today, I mean, there's already some great things in the news. There's some stuff that we're doing. The Project Artemis is looking at sending human beings back to the surface of the moon. We just very recently had a rover that landed on the surface of Mars. We're getting some great data back from that. And I think we heard from a couple of additional space companies, Axiom Space and Intuitive Machines, talking about some things they're trying to do. Axiom in low Earth orbit, and Intuitive Machines is trying to return the United States to the surface of the moon. So lots of really good things going on in Houston related to space. But these types of missions are very different from trying to enable human beings to go to, say, the outer solar system, or maybe even onto another star, right? For example, if we wanted to send human beings to Saturn and we wanted to get them there in about 200 days, the amount of energy that you have to put into a spacecraft to achieve that kind of a mission is an order of magnitude higher than it takes to get a payload from the surface of the Earth to low Earth orbit. It's entirely different. Chemical propulsion, from a physics perspective, will not close that type of a mission objective. So in order to try and enable bold human exploration of the outer solar system and maybe one day onto the stars, it requires significant improvements in power and propulsion systems that we use for spacecraft to try to achieve that. So how do we achieve that? What are the tools that we could potentially bring to bear on such an audacious goal and try and solve this problem from a physics and engineering perspective? Well, this chart, this is our kind of what we call our capability chart. And this kind of covers the waterfront of options from known physics, known engineering on the left, spanning all the way over into unknown physics and unknown engineering on the right. So let me talk just a few seconds here about this stuff you're seeing. On the left, we've got a swim lane we call fission. And so this is based on known physics, known engineering. And this configuration from the little cartoon spacecraft there is where you would have a nuclear reactor providing power for the spacecraft, and it's providing that power to some type of form of electric propulsion. And so this electric propulsion would be ionizing a gas, xenon is typically used, ionizing a gas and accelerating it to generate thrust. And so this system is extremely fuel efficient, much more fuel efficient than chemical propulsion would be. And so when you talk about human space exploration with something like nuclear electric propulsion based on this fission process, you're talking, megawatt level type of powers. So if anyone's seen a locomotive go by at a train track, each one of those locomotives that goes by is about roughly 2 megawatts worth of power. So this particular concept, right, this architecture based on known physics and known engineering, there's no showstoppers here. This would enable human exploration of the outer solar system. There's no physics that would preclude that. And this would also enable what we call interstellar precursors. Maybe we want to go someplace very, very far out in our solar system. You see on the chart there, it says 1,000 astronomical units, 1,000 AU. An astronomical unit's like the distance from the Earth to the sun. And so if you kind of made a stick like that and lined it up 1,000 times, that's 1,000 AU. And for comparison, Voyager spacecraft, I believe as of this morning, might be at about 155 astronomical units away from the sun. So it's pretty far away, but it's definitely not interstellar. Now, if we move a little bit into the unknown, where we know the physics, but maybe we don't have the engineering figured out. We could change the power source from a fission-based reactor that's using uranium and go to a fusion-based reactor that's burning a plasma, a deuterium-tritium plasma, to generate power for those electric thrusters. And you see that in the top middle there, FEP, fusion electric propulsion. Alternately, you could potentially just have it arranged in such a scenario so that the fusion reactor just directly vents the plasma burning products directly into space and generate thrust that way. And so that's called direct fusion. Now, this is going to be a higher power level than fission. Certainly, it will enable fast human exploration of the outer solar system. And if anyone's familiar with the TV show Expanse, it's actually kind of the propulsion concept that they use to frame up that little story. Now, fusion, interestingly enough, is actually what's discussed in the literature to enable what I would call slow interstellar. I think there's a movie called Passengers with Chris Pratt and Jennifer, I can't remember her last name, but that movie, that spacecraft in that movie was based on fusion. And that's because fusion is discussed a lot in the literature as a way for us to get to a neighboring star, probably in the larger fraction of a century, if you will, 50 to 150 years, if you will. But this is, again, based on known physics, but we don't have the engineering figured out because we don't have fusion reactors anywhere on the Earth. The sun can do it, and it does it just fine, but we haven't quite figured it out yet. But the only obstacle there is just engineering. And then we get into the third swim lane, which I call breakthrough. And this is where we're kind of on the frontiers of physics, right? If you think about physics as a Venn diagram today, right, there's kind of two circles on that Venn diagram, and they kind of touch at one spot. And some of the words in one of those circles would say quantum mechanics, and that's the standard model of what governs the microscopic world. And we have cell phones and computers as a result of our understanding of quantum mechanics. And then in the other circle, you'd have the words general relativity, and that governs the macroscopic world, how the sun and the stars and the galaxies evolve over time. But from a practical technology perspective, global positioning satellites, the GPS concept is as precise and accurate as it is because we correctly factor in all of the mathematics associated with general relativity. So just based on known physics and known engineering, right, we have cell phones, and we can use those cell phones with a GPS to navigate to go see a friend at a new restaurant, if you will. So just that level of physics touches our lives every single day. But those two models don't fully overlap with one another on the Venn diagram. So there's a more generalized understanding for us to get. And so in the process of trying to decode some of that unknown physics, maybe we can find ways to interact with the vacuum of space or space-time itself. We can find some way to attractively generate a force. And so this is discussed in the literature as perhaps maybe a concept of a space drive. We know from general relativity, there are things that mathematically we understand as wormholes or space warps. And that's a way to maybe get somewhere very, very quickly without violating the speed of light and still make it a quick trip. Mathematically, we know how to do that, but we don't know how to build something to do that. And so working on the frontiers of physics, maybe we can figure out ways to reduce that to practice. So here at LSI, we are a doing organization, right? We want to go through and accomplish things as we go through the process of inspiring and educating the next generation. And so, this is all based on fostering and supporting R&D. And so we conduct research and development internally through something we call EagleWorks Laboratories. We're currently funded by DARPA Defense Science Office, doing some foundational work. I'll talk just a second about that. We also commissioned in the middle of last year something we call Interstellar Initiative grants. We are in partnership with Texas A&M the breakthrough initiatives with that particular endeavor. We received proposals from universities and organizations from all over the globe. Went through a rigorous peer review process and selected 9 grant performers covering topics from beamed energy propulsion, relativistic solar sails, fusion propulsion, space drives, and wormholes. I'll talk a little bit about each one of those in just a second. For awareness, we actually have a YouTube channel. We just conducted a midterm public brief where our performers were giving us an update on the midpoint of their project. And so you can go to our Limitless Space Institute YouTube channel and see the replays of that. We recorded all that. We also have something called University Partnerships. That's where we partner with universities to kind of jointly work on research topics in this advanced power propulsion that we consider of value to both organizations. We're currently engaged with Texas A&M, working on a micro nuclear reactor that's in the 1 to 10 megawatt electric range. And so we're always looking for new opportunities to partner with universities. Student programs and education outreach. This summer, we'll be teaching a class on interstellar studies. We commissioned the Initiative for Interstellar Studies over in the UK to help us to develop this classwork. They've done a number of classes at the International Space University. So we're really looking forward to that. That'll be really neat. So that'll be advertised on our website in about another week or so. So this is our NASCAR chart. This goes through and shows just within the last 18 months, the organizations that we've been able to formally create a relationship with, some of which through the grant program, the EagleWorks program, university partnerships, and we anticipate this growing as we continue to move forward. We have lots of discussions already in place, and so we're really pleased to be able to engage with all these entities and universities from all over the planet that have a similar desire to kind of really push the boundaries of what we know and push back the darkness, if you will. Just a couple words here on the work that we're doing within EagleWorks. We're currently funded by DARPA Defense Science Office. This is definitely in that third most swim lane breakthrough. We're doing some foundational research on something we call our dynamic vacuum model. We're fabricating some customized Casimir cavities. You can kind of see from a little slide there. This is a scanning electron microscope image of some of the very complicated geometry that we're building down at the nano/micro level. This is very challenging. We're partnered with Texas A&M on this endeavor, and Isentis is up at Boston using the MIT nanofabrication facilities up there. So this particular work, although it's basic science, does have the potential to have implications for power, maybe the ability to increase something we call negative vacuum energy density. That's kind of a necessary ingredient for the idea of a space warp or a wormhole. It may have some potential communications and sensors applications, and it may also be a potential early form of a space drive. It remains to be determined what level of performance we could get out of that. So, switching gears to the Interstellar Initiative grants, I'll just give a 30 seconds or so on each one of the projects. So Interstellar Initiative grants is a biennial program. We want to run this about every 2 years. And the way it works is we have a 12-month period of performance for the grant performers. We fund 2 categories of work. We have one we call a tactical grant that's anticipated to be predominantly like a paper study. Occasionally it could be a laboratory study if it's a mature program where they have other partners. And then we also have a category we call strategic grant, and that's up to about $250K, and that's definitely where we want to tie to some empirical work, if you will. And so now I'll just skim through some of the grant performers. So we have Professor Phil Lubin at UC Santa Barbara working on something called directed energy for revolutionary space propulsion and power projection. This is kind of beamed energy propulsion, if you will, where you have some type of a beaming station that's beaming power to a system, and it's either using it for propulsion or it's using it for power. So the stuff that we're funding him to do is to try and mature the system beyond just being in a laboratory on an optics breadboard, to have individual elements out in the field. We have 3 individual elements, like a sparse beaming source that's providing power to a target that's connecting with those with a phase lock loop system, and try and demonstrate that at long lengths There's some potential for follow-on work as well. They've been in discussions with Intuitive Machines for a possible early demo where maybe we could do something with a Nova-C spacecraft on the surface of the moon. We're also funding Professor Richard Norty at Delft University of Technology. He's doing some work on relativistic solar sails. Breakthrough Initiatives created a mission concept called Starshot. And the mission model is where you're trying to use a ground station to beam power to a solar sail to accelerate it to very fast relativistic speeds. And so one of the challenges is the sail has to be able to deal with that relativistic shift in the wavelength of light. And so Richard is doing some work to try and figure out some topology of how to make that sail at a nano level so that it can deal with that relativistic shift of any source power from the ground. Very, very innovative and creative work. He's making some incredibly large sails, 5 centimeters, that have these nano features that are amazing. So he's probably one of the global leaders in this, making large structures that have these very detailed nanostructures. We're funding Professor Ray Sedgwick at University of Maryland, working on a fusion concept. This is something that uses centrifugal confinement that's got like a shear flow stabilization. And so this unique particular approach focuses on using the what you call alpha particles from the fusion combustion process. And so we're funding the very early work to take the model from this from the low fidelity to a slightly higher fidelity to understand some of the additional parameters of what this model might look like as you try and think about how would you start to try and build and test this. We funded Professor Jason Cassabry at the University of Alabama, Huntsville to work on some pulsed fusion. This is like magnetic inertial fusion, if you will. And so the concept is to energize a target and generate a plasma ball and actually try and trigger fusion in the plasma ball. And so the potential for this thing to reach break even, if you will, they have a system that can potentially explore that break even, but this work that we're funding is the initial work to try and figure out the scalability, to figure out what type of improvements they would need to get from this blue area on this graph up into the yellow area where you're at a coefficient of performance greater than 1 from a fusion perspective. We're funding Kelvin Long at the Interstellar Research Center to work on a very advanced code to model some fusion ignition processes in some capsules for some concepts that have been discussed in the literature. And so we'll be able to use this software suite to evaluate historical mission concepts and also evaluate some new mission concepts based on this, this inertial confinement fusion, this ignition process. We're also funding Dr. Sethian Yu at Helicity Space in partnership with Caltech, University of Maryland, Baltimore County. Again, in all these things, we have lots of universities involved and students involved. It's great to be able to connect with the next generation this way. So Dr. Yu is working on a fusion concept that kind of uses something called a plectoneme. You can kind of see from the pictures the lead in here from these guns. They're generating these, looks like a donut rope of plasma. And so using these plectonemes, that's the fancy technical term, you can combine these things and actually generate this fusion process. And then this peristaltic nozzle goes through and exhausts the products out the back and increases the coefficient of performance. And so we're funding the peristaltic nozzle portion. This is also in partnership with some other entities as well. We're funding Professor John Bush at MIT. He's working, again, this is kind of the frontiers of physics. He's working on something called the hydrodynamic quantum field theory. He's trying to go through and figure out, in the process of understanding the nature of the quantum vacuum, can we potentially find ways to interact and generate a force and push off of the quantum vacuum itself. Additionally, we funded Charles Chase at UNLAB in partnership with Professor Yuval Dagan at Technion Israel Institute of Technology. They too are working on something that would be categorized as a space drive. They're also exploring the quantum vacuum, a slightly different perspective, but they're trying to figure out, can they use asymmetric potentials in this case, in the form of like a resonant tunneling diode. The resonant tunneling diode is predicted to interact with the quantum vacuum in such a way that it will generate a bias and an asymmetry in the way the vacuum fluctuations interact with the device. And this might be able to generate a thrust that we could use on a spacecraft. And finally, we've funded Professor Remo Garantini at University of Bergamo over in Italy. He's doing some work on traversable wormholes. He's well published in the literature exploring the idea of a wormhole. He's trying to figure out, are there some ways that we can use customized Casimir configurations coupled with using different types of materials, perhaps superconductors, to magnify the effect and maybe figure out a way to take it from just this mathematical abstract. How can we kind of move it a little bit more into the realm of at least feasible, if you will, or maybe it might be safer to say plausible, right? And then finally, switching gears away from the Interstellar Initiative grants, we have our university partnerships. As I said, we're partnered with Texas A&M to work on a micro nuclear reactor that's in this 1 to 10 megawatt electric range. It's a portable nuclear reactor. We want it to be something that would fit in a 40-foot Connex container. And that's not by coincidence. The Department of Defense has something called Project Pele. And so that too is also looking at developing micronuclear reactors that would fit in effectively a 40-foot Connex container that could be moved all around the globe for whatever purposes they had. But they're not setting the constraints for that reactor in a way that would make it compatible for spaceflight. And so we're working with the nuclear engineering department at Texas A&M to figure out, can we design a reactor that meets all the DoD Pele program requirements, but we've designed it in such a way so that all the subsystems and the materials choices and the arrangements make it easily adaptable for use in space. So can we find a way so that there is a terrestrial program that could help cover some of the the DD&T costs for something like this? It might make it a little bit easier to one day realize a nuclear reactor. If you think back to one of my earlier slides, those 3 swim lanes, nuclear electric propulsion was the leftmost swim lane that was based on known physics and known engineering, and it required a nuclear reactor that was in the megawatt range to be able to kind of open up the solar system, if you will. So I think with that, that's everything I had there. So at that, let me stop sharing my screen and see if there are any questions that came in on the chat. A nuclear reactor that was in the... Okay, let's see here. I'm looking at some of the questions here. Can the public view the research projects and talk with the scientists? So we have YouTube recordings of the Interstellar Initiative grants. We did live broadcast those. So there's 2 ways to potentially connect with those types of events in the future. We have a Zoom webinar where we can have people as attendees that can ask questions to the Q&A panel through the Zoom. And then we also have a YouTube live stream that we connect the Zoom webinar to. And so we monitor both those windows. So we were able to answer questions through the Zoom interface and from the YouTube interface. In terms of the university partnerships, we don't have that quite set up yet, how we want to handle that. But certainly the EagleWorks, I do a number of talks to interns and co-ops and so forth. Well, I will expand that type of stuff and have discussions like that. And then, of course, I try and make sure all the papers that we publish are open access. Let's see. Another question, is LSI working with other experts in industry or other universities? I think you saw from the NASCAR chart, we have quite a number of universities that we're already working with and a number of folks in industry. Certainly some of our cousin entities, if you will, because of our connection with Dr. Kambufarian, Axiom Space, Intuitive Machines, X Energy. Our board of advisors has a number of folks that in the aerospace sector and energy sector. So Chris Mowry at General Fusion. Let's see. Looking at some other questions here. What am I most encouraged by the current research? I think from the fusion perspective, fusion has often been discussed as it's always 20 years in the future, and it always seems to have been 20 years in the future. But folks that are familiar with the fusion realm, there are a few things that have changed in the last 10 years, specifically in the last 5. So the concept of a fusion reactor was kind of marching towards the fusion triple product that says we have actual break-even fusion at the same rate of Moore's law, if you will, all the way through in the mid-90s. But there was a problem with some of the material science. The superconducting magnets were not robust enough. And so I think part of that, you see the implications of that when you look at ITER, the big international fusion reactor that's about 10 stories tall. It's very expensive. It's based on some of the best anticipation of what superconductors could do for a fusion reactor. And so and when you look at the equations, one of the dials you can turn to make something work was size. And so in the 90s, they made the decision to go big. In the last 5-10 years, we've seen the development of REBCO, high temperature superconducting tape. This is a very robust high temperature superconductor, considerably more resilient than some of the previous stuff we've used, and can generate much larger magnetic fields than we ever thought possible. And so I think that's been a real game changer. And so you see there's MIT has spun off a commercial company called Commonwealth Fusion, working on magnetic confinement fusion, a tokamak reactor that's about 1/100th the volume of ITER, but will potentially have the same performance from like a physics coefficient of performance, right? So it's REBCO has kind of changed the game space, if you will, of fusion. So I think we will potentially see terrestrial fusion reactors in a lot sooner than we anticipated, and they may be a lot smaller than what we thought they might be when we think about ITER. Let's see. How do you go about testing methods for creating traversable wormholes? Is it done mostly through computer simulations? Certainly a lot is done through computer simulations. We're still trying to figure out all the subtleties of the mathematics. And then of course there's the matter of something we call exotic matter or negative vacuum energy. How do you make that? And so some of the work that we're doing with the exploration of the dynamic vacuum model, we're making these customized Casimir cavities that's manifesting something called negative vacuum energy density. It's kind of the thing that looks and has the same mathematical characteristics of what general relativity says is required for the idea of a space work. And so certainly there's simulations that we do, but there's also testing that we do to kind of explore the characteristics of that. First off, I think we'll probably be testing things just from an optical perspective. We won't be doing any kind of macroscopic demonstrations. It'll be very much kind of a sciencey affair, if you will. So another question here is: a vacuum energy system basically like turning Hawking radiation into thrust? Not per se, though. That's like the dynamic vacuum. Assuming that's like the dynamic Casimir phenomena. That's a separate mechanism. The stuff that we're doing is kind of looking at the fundamental nature of the quantum vacuum itself as a field that we can potentially interact with. I think it's a little bit more sophisticated than we've typically considered. We've had a lot of success modeling things like the hydrogen atom and trying to understand just from things that we already know, how does it map to that? And then with those insights, does that allow us to potentially make new predictions for things that we could potentially explore in the lab? And that's part of what we're funded by DARPA Defense Science Office to do. Great question here. What are the expectations regarding the timeline to deploy these funded research projects into real hardware? Right, that's a great question. What's the crawl, walk, run type of mentality? Are we thinking about that? And so some of this stuff is definitely basic research, and it's hard to extrapolate too far forward. But some of it's a little further along where you could potentially connect the dots. The beamed energy propulsion from Professor Phil Lubin at UC Santa Barbara. There may be a way for us to do an experiment with a 10-meter diameter ground station, sparse populated ground station with a series of sources that, Phil Lubin already has designs for these sources. He could beam a signal to a spacecraft on the surface of the moon, in this case, potentially the Nova C spacecraft. And then that 10-meter diameter sparse array would not be able to beam power directly to the Nova C spacecraft because it would be too diffuse. But what it would do is it would heat up the lunar regolith. The diffraction pattern of that sparse array would heat up the lunar surface and create little hot spots in the form of like little polka dots, if you will. And so the Nova C spacecraft could have like an infrared camera looking out over the lunar regolith and see the spots on the surface of the moon. And that might be a really interesting thing to see. But that would be like a precursor demo. Also, we've talked to Intuitive Machines and Axiom Space for some ways to maybe test Professor Richard Norty's relativistic solar sail concept. He's got that 4.5 centimeter by 4.5 centimeter sail, and that's potentially something we'd like to discuss testing with a 100-watt beaming source on a spacecraft that's in orbit. Try and shoot that sail to the moon or something like that. That might be a very interesting demo to do as a precursor. So I think we're at time now. It's 11 o'clock. Thanks everybody for joining me today. I'm going to go ahead and shut down the live stream, and thanks everybody for participating. Have a good rest of your Thursday. Try and stay dry. We're certainly getting a lot of rain here in Houston. Be safe. See you guys.